In the introduction to this course, I said that some devices used feedback paths that take output signals and reuse them as inputs. The combinatorial circuits that we've been looking at so far don't involve any feedback, but adding this single modification opens up a whole new range of possibilities based on the fact that a circuit with feedback can remember a data value. The simplest possible case of feedback paths would be a circle of wire with no resistance, which can actually exist at very low temperatures. If we establish an electrical circuit, an electrical current in such a wire, it will flow forever, or at least until the temperature increases, and we could say that the direction of the current represents a bit of data. 0, let us say. If the current were flowing in the opposite direction, then the wire would be remembering a 1. Well, practical memory devices involve a more complex arrangement than a circle of wire, but feedback that allows a data value to cycle around a circuit is still present in these designs. The more complex practical designs have two modes: a memory mode in which data is remembered and can be read, and a load mode in which a new data value can be stored in the device, where it will stay until it is overwritten. The simplest practical devices that are used for memory storage are called, rather charmingly, FlipFlops, because they can exist in one state and can also be loaded with a new data value to flip, or flop, them to the other state. Of course, there's nothing to prevent the new data value that's loaded being the same as the old data value, in which case the output value wouldn't flip at all, but never let it be said that such mundane considerations got in the way of a catchy name. A flip-flop should be capable of being loaded with a bit of data, either a 0 or a 1, and retaining that information until a new data value is loaded into it. Up till now, we've designed circuits by working through a standard sequence. English language description leads to truth table, leads to Boolean expression, leads to combinatorial circuit. This time, for a change, we'll start at the other end with the completed circuit and demonstrate that it has the desired behavior. The circuit will use NOR gates. We haven't seen NOR gates in this course before, but they're quite common. They're an OR gate that inverts its output. The circuit symbol is an OR gate symbol with a little circle on its output to symbolize the inversion that happens there. To characterize the behavior of a NOR gate, we can draw up a truth table. It's easier to follow if we draw it up in terms of voltages rather than true and false or 0 and 1. Like any OR gate, the NOR gate distinguishes between the input combinations with two low inputs, which in this device produces a high output, and all other input combinations, which in this device produce low outputs. To remind us of this behavior, I've written a little mnemonic on the left-hand side of the screen. Any highs produce a low. Now, we know how the individual gates behave, so let's have a look at the complete circuit. It involves a feedback path. The output signal from the first NOR gate is fed back as an input to the second NOR gate, and the output signal from the second NOR gate is fed back as an input to the first NOR gate. These inputs are labelled R and S. The circuit is completely symmetric, so it's quite arbitrary which is which, and we label the outputs Q and not Q. These names aren't allocated in quite such an arbitrary way. Q is output by the NOR gate with the input called R, not Q is output by the NOR gate with the input called S. And the fact that we've called them Q and not Q implies that we want their values to be inverses of each other. We'll come back to that point later. In the meantime, we need to get started on analysing the behaviour of the circuit. Now, that's more easily said than done, because the outputs of these gates depend on their inputs, and from the outside we can only set one input to each gate. I'm going to draw up the transition table so that it looks as though the values in the table are driving the input wires of the circuit directly. We'll start our table by showing the situation when R and S are both 0. But the other input to each gate comes from inside the circuit, so how do we cope with this? Well, we simply consider two separate situations separately, first where it's a 0 and secondly where it's a 1. And because the circuit is symmetric, we only need to consider the output of one of the gates. Let's make it the left gate, the one that's outputting the signal we call Q. We'll start with a 0 output from Q and show this value also in the table where there's an entry for Q. I've connected this into the table with a dashed line to indicate that the table is not actually setting this value. And in fact, since the value on this output is controlled by the circuit, it could change. So the value we assume to start with may become invalid during the operation of the circuit. And that's why I've labelled the column in the table, or this column in the table, as Q subscript T. That's to indicate that it's the value of Q at a particular time. At some time t, the output Q has one value, and a short time later, at time t plus 1, its value will be, or at least may be, different. We'll put that value into a separate column in a moment. Note that I haven't defined the units of time. T plus 1 isn't 1 second later, or a microsecond, or a millisecond. It's a reference to some arbitrary time delay that it takes the electronic circuit to settle down. So we write down the value of Q at time t, and once we've worked out what it is, we'll write down the value of Q at time t plus 1 to show how the output from the circuit changes. So now let's get back to working out what the output actually will be. The right-hand NOR gate has two known inputs, both low voltages. We know that if there are any highs, a NOR gate produces a low output. There aren't any, so it produces a high output. That high voltage travels along the wire to become the second input to the left-hand NOR gate. That gate now has one high input and one low input. Our mnemonic tells us that any highs produce a low, and we have one high, so the output of the left-hand NOR gate is a low voltage. Well, of course, that's what we assumed in the first place. So what we have here is a stable situation. If Q is low, as we assumed, and we set R and S to be low, then the output of Q remains unchanged. In other words, Q at time t plus 1 is a low voltage, and not Q is a high voltage, the opposite of Q, which is as it should be. Now we can move on to deal with the second case. R and S are both still low, but this time we look at how the circuit will behave if the output from the left-hand NOR gate is a high voltage. Let's put that into the transition table. So now the right-hand NOR gate has one high and one low input. Remembering that any high produces a low, we can see that the output from that gate will be a low voltage. The left-hand NOR gate therefore receives two low inputs, which makes it produce a high output. That's consistent with the value that we assumed for Q in the first place. That is, after the initial high value of Q has remained, the initial high value of Q has remained unchanged when the R and S inputs are both low. And of course, the not Q output is the opposite of Q. Can we see a pattern in the behavior listed in the transition table so far? Oh, by the way, we call it a transition table and not a truth table because it specifies the transition between an old value and a new value of output. So, where's our pattern? In the first case, the old value for Q, Qt, is the same as the new value for Q, Qt plus 1. That is, they're both low. And in the second case, Qt and Qt plus 1 are both the same. So, in other words, whether Q is high or low to start with, it remains unchanged while R and S are both low, and the output is thus stable. This is therefore the memory mode of the flip-flop. If at some earlier time we've managed somehow to set the value of Q to be a 0 or a 1, this is called loading a value, that value will be retained or remembered by the circuit while R and S are both low voltages. Now let's start looking at situations where R and S differ from each other. Let's start by making R low and S high. Q might be high or low, so we'll start by considering the case where it's low. The right-hand NOR gate therefore receives one low input and one high input, so it outputs a low. So the left-hand NOR gate has two low inputs, and consequently its output is high. Now, that's different from the value that we gave it to start with. Does that mean that we gave it the wrong value? Well, no, it just means that the output from the gate has changed. Now, this has all taken place in something like a thousandth of a millionth of a second, so we don't want to get too excited about it. But it does mean that the input to the right-hand gate has changed, so we need to keep on with our analysis to see what happens next. Let's hope that the outputs don't keep jumping up and down. That would be what the analog engineers call oscillation, and it's by no means a desirable property in a memory circuit. So what does happen? Well, nothing much as a matter of fact. The right-hand NOR gate now has two high inputs, whereas previously it had one, so it still produces a low output. At this point, therefore, the circuit has settled down. Q subscript T plus 1 is high, and not Q T plus 1 is low. But remember that any time that an output changes, your analysis hasn't finished, and you need to keep on tracing the voltages around the circuit until they've settled down. Fortunately for us, the circuit never goes into oscillation. The outputs do always settle down. So after reanalyzing one gate, sometimes after reanalyzing both gates. So since this same principle is at work for each row of the transition table, we won't bother to talk through the details of the remaining rows. It won't do you any harm, though, to work through it as an exercise to assure yourself that you can predict the values in the rest of the table. However, now that we've listed all the outputs that are produced where R and S differ, we can search for a pattern. Here it is. The new value of Q at time t plus 1, is equal to the value that we input as S. So we can say that we've loaded S into Q. Or if you like, we can say that S is used to set the value of Q, and that of course is why it's called S. And the new value of not Q at time t plus 1 is equal to the value we input as R. So we've loaded R into not Q. This is the set-reset behavior mode of the flip-flop, and it's used to load it. We tend to think about S and Q as the important input and output, and we say that we set the value of Q to 1 by making S 1, and we set it to 0 by making S 0. But of course, we've also got to make R the opposite of S, and not Q ends up being the opposite of Q. But it's easier to think of S as the input that sets Q to a particular value, and then sort of whisper to yourself, and that means that Q and not Q have to have those other values, whatever they are. Right. On to the last category of input combinations, when R and S are both high. We've already seen the device in memory mode and load mode. What more can there be? Well, unfortunately, something that we don't want at all. When R and S are both high, our analysis will show that the circuit makes both the new value of Q and the new value of not Q low. We definitely don't want that, because we want Q and not Q to be the opposite of each other. Always. So, since the other input combinations have all the behavior that we want, we say that this input combination is forbidden. We've designed a circuit that can load a bit of information and store it, but we have to avoid some input combinations because they generate an inconsistent output. That's not really a very satisfactory situation. We'd really prefer the circuit to behave sensibly under all input conditions, so that leads us on to think about problems with RS flip-flops. First of all, let's list the one we know about. When the device is storing a bit of information, its R and S input voltages are both supposed to be low. However, the inside of a computer is an electrically noisy environment. Transistors are switching on and off all over the place, and that generates electrical interference. If that causes a momentary high voltage on the R or S input of a flip-flop that's supposed to be in storage mode, then, for instance, it changes to load mode, with R and S different, and it will load a new value. That new value may be the same as the old value, or it may be the inverse. There's a 50-50 chance. You don't want the top digit of your bank balance to change from a 1 to a 0 with a 50% probability if there's a bit of electrical interference in the processor chip. So, RS flip-flops are problematic because the value they contain can be corrupted by a momentary high voltage called a glitch on one of the inputs. Secondly, we're designing a large computing device, so we may want to use a single shared delivery path to feed information into a whole lot of storage devices. If the data values control the load behavior of all the flip-flops, and the same data values are presented to all the flip-flops, then they'll all load the same information simultaneously. There's not a lot of point in having the same value stored in all the flip-flops. We'd prefer to control them so that each one can be loaded independently from that data path. The way to do this is to unbundle the control signals and the data supply. Whoever designed the RS flip-flop probably thought it was pretty nifty to get a single pair of wires to perform both functions, but in fact it's made things more complicated. If we separate control and data, then the flip-flops can still share a single data path, but each one can be given an individual control input that tells it when to load new data. So, as I say, the way to do this is to unbundle the control signals and the data supply. We do know of one device that could cope with this problem. Demultiplexers are designed to deliver a bit of data to one of a number of possible destinations. Isn't that the situation we have here? Well, yes, we could set up a demultiplexer to deliver the R bit and another to deliver the S bit to a specified flip-flop. But that's a heavy-handed approach in this situation. Or if you prefer, there is a way of handling this problem more simply and at less cost. So why, if RS flip-flops have all these problems, have you been taught about them? Because the new improved version doesn't have a completely different circuit. It's an RS flip-flop with an extra little bitty that makes it behave more acceptably. We call this new improved version the clocked RS flip-flop. Now, the word clock is a new term in this context, and it's a pretty important one in computing, so we'd better make sure we know just what a clock means to a computer. Pretty nearly everyone knows that their computer has to have a clock somewhere in its innards. That's how it can display the time of day somewhere on the screen. But there's more to a computer's clock than that. If we're going to understand what it's doing, we need to distinguish between two ways that clocks are used. The most common usage is to tell us what the time is, that it's 2:17 p.m. or 3:08 a.m. or whatever. But there's another, more fundamental reason for clocks. They tell us when it's time to do something. If you and I have organised a meeting to discuss how we're going to murder Jim, it's important that we turn up at the meeting, and that Jim doesn't turn up. It doesn't matter whether the meeting is at 2 p.m, 9 a.m, 7:15 p.m. or any other time, so long as we both turn up and Jim doesn't. So the primary information we're getting from the clock isn't the time of day. It's scheduling information, whether or not it's time to do something. And the clock in a computer is used primarily to schedule activities inside the processor, to make sure that one component loads data at the same time as another component is outputting the data, for example. You ought to make sure that a calculating component has enough time to complete a calculation before the output is used. So the clock input to a flip-flop isn't used to tell the flip-flop that it's 10 to 7, or even that 10 microseconds have elapsed since some prior event, but simply to make the flip-flop load some data right now. That's a pretty abstract interpretation to put on the word clock. And if you already know something about the architecture of PCs, it may even seem to contradict something that you already know. That the clock on a PC is running continuously at a speed that's measured in gigahertz. In other words, that the clock inside a PC ticks regularly thousands of millions of times a second. What's the point, you might ask, of loading new information into a flip-flop thousands of millions of times a second? Well, the answer is that the input called clock that the RS flip-flop uses isn't driven by a signal that ticks thousands of millions of times a second. It's connected to some control circuit that specifies when the flip-flop is to be loaded. Now, the control circuit usually has a regularly ticking input, but the control signals that it generates aren't on such a regular schedule. It's like a stage manager at some complex events like the opening ceremony at the Olympics, for example, sending signals to various groups of performers on the field. Flag bearers, go. Go with the human pyramid. Start the Mexican wave now, and so on. Later on in the course, we'll talk about how to design a control circuit that behaves like this. In the meantime, let's just get back to the matter in hand, designing a clocked RS flip-flop, an electrical circuit that will load a bit of data when it's told to, and will store that bit of data till another bit of data is loaded and replaces the first one. So, at long last, let's start building the circuit for a clocked RS flip-flop. It incorporates the circuit we've seen already, and there's a clock signal that enables a couple of data inputs to get through to the R and S inputs of the flip-flop. Now, this way of thinking about AND gates is something that we haven't encountered before. Previously, we've been able to treat the inputs to an AND gate as a couple of indistinguishable bits of data. Now, however, we're looking on one input, the clock input, as a control signal, and the other input as the data. If you review the truth table for an AND gate, you'll see that if you treat either of the inputs as a control input, then the output of the AND gate is false when that control input is a low voltage, and the output of the AND gate is equal to the other input when the control input is high. In other words, the control signal allows the data signal through the AND gate when it's high, and it forces the output of the AND gate to be a low when it's a low. So in the circuit we're looking at here, when the clock signal is low, then it doesn't matter what R' and S' inputs are, because the inputs to the RS flip-flop are both low. So it's in memory mode. When the clock input is high, on the other hand, the data inputs R' and S' get through to the RS flip-flop. And by making R and S different, we can load a new value into the flip-flop. Now, we know that there will be periods during which the data is being loaded into flip-flops and periods when it isn't. And if we do know that, then we can design the computer so that the calculation, which causes voltage glitches, and flip-flop loading, which is sensitive to glitches, happen alternately. That's at least a partial solution to one of the problems we mentioned earlier, that RS flip-flops are susceptible to loading unintended data values when glitches occur. We also said that we'd like to be able to supply a large number of flip-flops from a common data source, but load only one of them. The clock input allows us to do that. Any number of flip-flops can share the R' and S' inputs. But if each flip-flop has its own clock input, then we can load the flip-flops independently. So that's a distinct improvement on the original unclocked RS flip-flop design. The clocked RS flip-flop has been used in commercial computer designs. However, Glitches can't be eliminated altogether, and as computers got faster and smaller, the frequency with which they occurred increased to the extent that the probability of corruption of the data became unreasonably high. And there seemed to be too many wires going into the flip-flop. We only want to be able to load a bit of data and store a bit of data. Surely 3 inputs is too many. Something, as they say, needed to be done. That brings us to the next step in the saga, the D flip-flop. A D flip-flop uses the fact that when the clock signal is low, the R and S inputs are held low, whatever the values of R and S happen to be, to simplify the circuit so that it has only one single data input. So we can quite happily allow R' and S' to be different all the time, and they'll only get loaded into the flip-flop when the clock is high. So instead of having separate R' and S' inputs, we use a single input which we call D for data. That replaces S', and we connect an inverter to D and use it to generate the R' input. Now the AND gates always get a pair of different values. They may be 0 and 1 or 1 and 0, depending on the value of D, but whatever they are, they'll only get through to the AND gates and loaded into the flip-flop when the clock signal is high. So when the clock signal is low, the AND gate forces the R and S inputs of the RS flip-flop to be low, and thus puts it into memory mode, retaining the 0 or 1 that was last loaded into it. And when the clock is high, the AND gates allow D and its inverse through as S and R, so that the flip-flop loads a new value. Furthermore, the inputs R and S can never both be 1 simultaneously because of that inverter, so the RS flip-flop is never presented with the forbidden input combination of 2 high voltages. So, to summarize, this new circuit has no forbidden input state, it can be independently enabled, and its susceptibility to glitches is significantly reduced by comparison with the unclocked RS flip-flop. Nevertheless, its susceptibility to glitches has still not been reduced to 0. There's still room for improvement. To reduce glitch susceptibility still further, we move on to the edge-triggered flip-flop. This is designed to allow data into the flip-flop only when the clock signal is transiting from a low voltage to a high voltage, or from a high voltage to a low voltage. If we look at a plot of voltage against time for some incredibly noisy data, and a clock signal that's used to load the data, we can see that a D flip-flop that loads when the clock voltage is high could easily pick up the wrong value. But if we pick up the data only at the instant when the clock signal is going from a high voltage to a low voltage, then the time when the circuit is susceptible to glitches is much less than before. And we can also play the same trick that we played before, taking a great deal of care to design the computer so that the glitches are highly unlikely at the moments when the clock is transiting. This approach almost eliminates susceptibility to noisy data, sufficiently to make it the approach that is used in modern computers. The particular flavour that we've drawn here triggers a load when the clock signal is changing from a high voltage to a low voltage, and is called a falling edge triggered flip-flop. Rising edge triggered flip-flops can also be constructed. We won't spend time looking at the details of the edge triggered flip-flop mechanism. They aren't more complex than the other circuits. You just put a couple of crossed over feedback paths around a standard flip-flop and you'll find that analysis similar to the one we conducted earlier for the RS flip-flop will reveal the edge triggered behavior. We're only omitting this analysis because it takes a while and because it's so similar to something we've already covered, and it doesn't add a great deal to our understanding of what's going on. Instead, we'll move on to one more type of flip-flop, and this one's the last, I promise you. The JK flip-flop is an interesting beast. Like the clocked RS flip-flop and the D flip-flop, it has an RS flip-flop inside, and some extra circuitry that controls the signals that get through to the R and S inputs of the internal flip-flop. That extra circuitry comprises a clock signal and a couple of AND gates. Those AND gates allow the input signals J and K through to the RDS inputs, but this time they're under the control of the outputs, Q and not Q, because those outputs are connected back to the inputs in a crossed over configuration. This results in a very interesting behavior, which you might like to prove by using the sort of case-by-case analysis that we used for the original RS flip-flop. You remember, we set R and S to particular values, assumed a value for Q, and traced through the circuit to see how it behaved. Well, you can do the same thing for this device, and you should come up with the following behavior. If the J and K inputs are both low, the new value of Q is the same as the old value of Q. The output of the device is stable, so it's in memory mode and will remember a single bit of data. If J and K are different, then a careful comparison of the table reveals that Q has become equal to J and not Q has become equal to K. In other words, we can set and reset the value of Q. And of course, not Q is always its opposite. Well, that's fine, but so far the device is behaving just the same as an RS flip-flop. What's the point? Well, the point, of course, is associated with that input combination which we said was forbidden for the RS flip-flop. In this circuit, if J and K are both high voltages, and the value of Q is inverted. If it was high, it becomes low. If it was low, it becomes high. And in this circuit, not Q is always the opposite of Q. So we've avoided the illegal behavior that plagued us with the RS device. So the new behavior that this circuit introduces is the ability to invert the output of the flip-flop. This is called toggling, by analogy with the two-position electrical switches with a toggle lever that gets moved up and down to switch something on or off. So what's the point of that? Well, it turns out that toggling behavior is very useful in an important class of digital logic circuits, counters. When we're counting, up or down for that matter, each digit of a new number depends in some way on the digits of the old number. Sometimes they're the same, so we need a circuit that can remember bits, and sometimes they change, which in a binary universe means that they toggle, change from a 1 to a 0, or from a 0 to a 1. But before we get on to talking about counters, let's just review how flip-flops are used. There are three things that we can vary: the type of flip-flop, whether the flip-flop is clocked or not, and whether the clock is level-triggered or edge-triggered. Let's start with the basic flip-flop categories. Simple RS flip-flops have the memory function that we need, but they also have problems that we've seen, so we never use them except as components of other, better flip-flops. D flip-flops are the standard workhorse devices for storing data. If that's all you need to do, use a D flip-flop and don't go for the more complex JK device. But that brings us to JKs. They store data and have an extra toggling function. Use them only if you need a storage device whose output can toggle. You can, of course, use them for simple data storage, but years of experience have taught me that people make far more mistakes when designing simple storage with JK flip-flops than with D flip-flops. So I emphasize, use JKs only if you need a device that can toggle. Let's move on to the second dimension of variation between flip-flops, whether or not they're clocked. Unclocked devices have to be controlled by their data inputs. This conflation of data and control inputs means that we can't attach a lot of flip-flops to a common data source and load them independently. So unclocked flip-flops are hardly ever used. And clocked flip-flops are almost always used, because they allow us to control when data is to be loaded. And that brings us to the final dimension of flip-floppery, the type of clock. Level-triggered clocks are hardly ever used, because they open the flip-flops to loading invalid data values. Edge-triggered flip-flops are nearly always used because they are so much more robust. So, overall, we'd most often encounter D or JK flip-flops according to whether we need simple data storage or data storage plus toggling, and they'll have clocks, and the clocks will be edge-triggered. Now that we've seen how to design a circuit that can remember a single bit of data, we need to figure out how to combine a number of those circuits together so that we can remember larger chunks of data. As you're aware, computers generally operate in terms of multiples of 8 bits. 16 was common for a long time, and as I write these notes, 32-bit machines are being superseded by 64-bit machines. So, if the computer transfers information around in 32 or 64-bit chunks, then the memory devices it contains need to be able to save and retrieve 32 or 64-bit amounts of data in a single operation. So one of the things we'll be looking at in the next little while is setting up storage devices so that we can handle words of data. We'll deal with 4-bit words rather than 32 or 64-bit words because we can extend the techniques that allow us to deal with a 4-bit word to any size word. 64 bits, 128 bits, even 1024 bits if we wanted to. The other major thing we'll work on is organising these words of storage so that we can get one specific word of data out of thousands or millions. Again, just as we'll restrict the size of the words to 4 bits, so we'll also restrict the size of the random access memory device we'll design to 4 words, because that's small enough to fit on the screen, and the techniques used to design it can be extended to larger memory sizes. However, we're getting a little ahead of ourselves. Before we get on to random access memory, RAM, let's look at a couple of other uses of flip-flops. A while ago, we considered the possibility of attaching a number of flip-flops to a single data source so that they could be loaded independently. This requires a set of independent control lines, each one clocking a separate flip-flop. Remember that the clock input to a flip-flop doesn't tell it the time, it tells us that it is time to load a data value. So when a clock edge occurs on load 1, for example, the second flip-flop in the array will load a new data value, and Q1 will become equal to whatever value was on the data input. The outputs from the other flip-flops will remain unchanged. We'll use that style of circuit a number of times in our design of a small processor, but for now there's another little design that looks very similar, but does more or less the inverse sort of job. This is the register. Registers occur inside the computer processor. They're typically faster than RAM, and they're used to store the temporary results of calculations and other information that the processor needs to access very fast and very often. They store multiple bits of data, so they require a number of flip-flops. And since those bits of data are loaded simultaneously, they share a single clock input, but have separate data inputs. Note that that's just the opposite of the earlier circuit. To repeat, in the first circuit, each flip-flop is independently loadable from a single data line, whereas the second circuit, the register, will load all the bits of a 4-bit word of data at one time when an edge occurs on the clock input, and all the flip-flops are thus clocked simultaneously. And of course, all the outputs, Q0 to Q3, assume new values simultaneously. So this circuit is always driving its output wire to a particular voltage, high or low. And if we connect several devices based on this design to a single output wire, then we'll get the sort of electrical conflicts that we discussed before. What to do? Well, we need a circuit that can sometimes disconnect its output wire from both high and low voltages so that something else can control it. To turn the inverter circuit, and remember that the other devices have the same general architecture, so this approach will work for more complicated gates as well. To turn the inverter into a tri-state device, we have to be able to isolate its output wire from the high and low voltages. We'll add a control signal called output enable to the circuit. That will operate an active low transistor so that when OE is high, the output can't be connected to the high voltage power supply, whatever the value of the data input. And the output enable control signal gets fed through another inverter, an inverter inside the main inverter if you like, to a second isolating transistor. This one is active high, for reasons that we won't go into in this course, and when OE is high, this transistor also turns off, so that the output wire can't be connected to the low voltage power supply either. So when OE is high, this new internal piece of circuitry completely isolates the output from either high or low voltage power supply rails. And when it's low, both of the transistors in the middle of the diagram turn on, so whichever one of the outside pair is turned on gets to determine the voltage on the output. This type of circuit is called a tri-state device because its output can have three different states: high, low, and unconnected. Electrically, that last option is called a high impedance output, and the electrical symbol for impedance is Z, so it's labelled high Z. The two inputs have different functions. The data input determines whether the output should be true or false, and the OE control input determines whether any Boolean output exists at all. So, if we incorporated tri-state circuitry into D flip-flops, we could connect the outputs of any number of them to a single bus, and by output enabling only one of them at a time, prevent them from causing electrical conflicts on the wire. And of course, data can be loaded from the same bus too. Now let's go back to the first circuit. We've seen how we can use a single wire, it's called a bus by the way, to deliver data to a set of flip-flops. What about getting the output from all those flip-flops onto a single conductor? This turns out to be a slightly more complicated problem. The outputs of all the flip-flops are being driven all the time. That is, each flip-flop is trying to set the voltage on its output, and thus on any wire connected to its output all the time. So if we just connected up all the outputs with a single wire, as shown in the diagram, there'd be a conflict. Boolean operators always have a true output or a false output. In electrical terms, that means a high output voltage or a low output voltage. So some flip-flops would be trying to set the voltage high, and at the same time, some other flip-flops would be trying to set the voltage low. That would have two undesirable consequences. First, the voltage on the wire would be indeterminate. It would depend on an electrical property called the output impedance of the flip-flops, and the ratio between the number of flip-flops trying to set the value to 0 and the number trying to set it to 1. And secondly, because some flip-flops would be supplying current to set the output voltage high, and some would be sinking current to set it low, it would cause the flip-flops to overheat, possibly with a bang and a puff of unpleasant-smelling smoke. To resolve this situation, we need to invent a new piece of circuitry. This involves little electronics, the only piece of real electronics in this course actually. First, we need to examine how transistors behave, because they're the components inside a flip-flop, or indeed inside any piece of digital logic, that actually set the output voltage. Here's a schematic diagram of a transistor. It will conduct electricity from the top of the diagram to the bottom of the diagram, but only if that vertical bar on the left is connected to a high voltage. That's typically 5 volts or 12 volts, by the way, not the sort of high voltage that will give you an electrical shock. Now, if we connect the bottom of the transistor to a low voltage, ground in fact, 0 volts, and the top to a wire, then there's no connection between the point at 0 volts at the bottom of the transistor and the wire at the top. until we connect an input wire to the vertical line on the left and make its voltage high. That is, when the input on the left is a high voltage, the transistor can conduct electricity from top to bottom. Then the wire at the top would be connected to ground, and its voltage would be, as we say, pulled low. So if that wire was used as the output of the circuit, we've got a way of giving it a low voltage, by connecting the input to a high voltage. Now that sounds a bit like an inverter, a circuit that implements a Boolean NOT operator, and in fact that's just what we've started to build. However, it's only half the circuit. It has a way to ensure that the output is low when the input is high, but it doesn't yet have any way of making the output high when the input is low. To do that, we connect up a second transistor to the input and to a high voltage. Now, you can see that this transistor is a little different from the first. The little circle that you can see indicates that it becomes an electrical conductor when its input voltage is low. Otherwise, the top and bottom of the transistor aren't electrically connected. So now, when the input is low, the top transistor turns on and connects the output to a high voltage. So to summarize, when the input is low, the output is high. And when the input is high, the top transistor turns off, the bottom transistor turns on, so the output wire is pulled to a low voltage. This circuit has a pull-up transistor at the top and a pull-down transistor at the bottom. And this arrangement is the basis of the standard implementation of many Boolean operators, NOT circuits like this, and also AND gates and OR gates, exclusive OR gates, NAND gates, and so on and so on and so on. The other circuits generally have more inputs, so they're a bit more complex than the inverter. But they all have a pull-up section, which may include several transistors, and a pull-down transistor section, which may also include several transistors. Now, the important fact about all of this is that the output is connected to a high voltage by the pull-up circuit, or else it's connected to 0 volts by the pull-down circuit. It's never left unconnected.